Testing. Good afternoon. Okay, sorry, I'm ready now. Just now I tried to adjust the volume and I tried to look for buttons instead, plus minus, and then this is quite old-fashioned. They use a knob to turn the volume up and down, right? Have you seen a knob to turn the volume? Nowadays, handphone, all this, you have to press the plus or minus button to control your volume. And nowadays, even they don't have this jack for your earphone. They use Bluetooth earpiece. All right. Okay. Welcome to this ST2334 Probability and Statistics. This is for lecture group 2. I think most of you are pre-assigned or you are up for this lecture group. The lecture group timetable for lecture at least is Tuesday and Thursday from 2 to 4, at least on paper, all right? LT26, all right? And there's another lecture group, Tuesday and Friday, in the morning, 10 to 12, all right? You better assign, you better go to the lecture group that you register for, because at this moment, at least my understanding is that we keep the materials just limited to that particular lecture group. Like, for example, the lecture notes, the two lecture groups, although they cover similar topics, but the style, the way that to present may be different. So you saw two different types of lecture notes, but basically they are similar. All right? And at least mine is a PDF taken from the PowerPoint slides. I think the other one is taken from the sort of like a text file, a PC text file. Similar to you, I have not able to access to the lecture notes from the other group yet. All right, so, but my point is, basically, the lecture notes will be different. Webcast, at least for this group, for today, for Tuesday and Thursday webcast, yeah, there's webcast, all right? You don't have to ask, so there's webcast. But it does not mean that you don't have to come, all right? You see, I need some interaction with you. If there's an empty lecture theater, no energy, so the webcast will be very boring, all right? So I need your help. So I need your support, so you better come, even there's webcast, all right? And so the webcast is only available to this lecture group students, and you can only watch as many times as possible, but you are not allowed to download, all right? So you can watch, fast forward, but you have to watch, if you want, all right? My 1 cent advice, don't wait until the last minute to watch all the 20-something webcast files at the end or before your exam. You better watch it regularly. Maybe once it's available, you try to watch it if you want. But if you attend lecture, understand everything, no question, also not a good sign. All right? there varies a very wide spectrum of questions, right? One is really, I don't know what you're talking about, okay? Then you need to work harder. The other one is that you really inspired by what we discussed and have more questions, all right? Anyway, having questions is very good, all right? Getting the answers of your own questions even better from yourself, all right? Of course, if you really cannot figure out, you can chat with me or with the tutors. All right, although I said that the resources like webcasts or lecture notes are separate, at least at this point, only this group is separate. I think you can access to group 1 lecture notes as I was told just now. All right, but I think it may be changed. All right, but the tutorial questions and the tutorial groups are open to anyone who registered for this one. That means there's no distinction or no separate way to register for the tutorial. All 2 lecture groups will be treated as one. All right? So the tutorial questions also will be the same. Don't have for lecture group 1 and lecture group 2. All right? So everything will be the same. Continuous assessment also only common to both groups. There's a midterm test. Assessment. All right? So one midterm test, 30%. Sit in, and most likely, okay, it's in week 7. If we cannot arrange for week 7, we may have to go to early week 8, Monday or Tuesday week 8. But we target at week 7. Because we have 2 groups, most likely it will be in the evening or on Saturday. All right? We try to see whether we can get the venue. All right? All together. And the rest is final exam, 70%. Any questions so far? Any questions? Yeah, good. At least no, right? Did I hit here correctly? No, right? You see? Are there any questions? Answer yes. Answer no. And no response. That's the worst. All right? So I want to have your responses. All right? Oh, by the way, I have those at the back. Can you hear me? Huh? Okay. Because for those who are not here, for the benefit of those who are not here, wait for the webcast, make sure that the voice has been recorded through this microphone. All right? So make sure that you can hear, then that means those who watch webcasts can also hear. All right? Tutorial start week 3. And when the tutorial registration open? This Friday or next week? Huh? Today, okay. Okay, so today start the tutorial registration, so you go and register for your tutorials, all right? And I would suggest that you attend tutorial, all right? Okay, what else? Oh, I forgot to introduce myself. Hey, remember, I may set questions in the midterm test. Who is the lecturer? You cannot answer the question, then you don't get the credit. Okay, I'm Chan Yu Man. So, in fact, I have already uploaded this morning, upload this file, course description. And there's another file, it's called information sheet. All right, those basically tell you similar things. Information sheet tells you more about some rules. All right, this basically tells you who is your lecturer of this group and the list of references and the topics that we are going to cover. All right. Okay, basically, I will cover half or slightly more than half on probability. And then the other half will be on statistical inference. All right. To some of you, you may think that you have learned it in your poly days or in your JC days. All right. It looks familiar, but now it may be more in depth. Really want you to understand and know the concepts behind all this. All right. Maybe you can get by just plug in the formula and get the answer. But this time, it's more challenging questions. All right. Make sure that you understand the topics that we covered. All right. So for the statistical inference part, basically it covers the basic estimation limited to very simple standard problems, as well as hypothesis testing problems concerning about means and variance. Okay, this is the information sheet. All right. All right. You see, you have to. You access to your lecture webcast, all this to the group that you assigned or enrolled. All right? Oh, yes. So both midterm test and final exam is closed book. But you can bring in one piece of paper, A4 size. That's it. All right. Here is some tips about preparing your help sheet or cheat sheet. Make sure that you don't copy everything. Yeah, very smart. No restriction on whether it's handwritten or typesetting. Wow. 300 slides, just condense it onto one piece of paper and print it out. Yeah, can do that. Bring in the magnifying glass and look at it. Yes, good. Hey, you are supposed to study, revise before your midterm test or exam. The 1 hour, 2 hours of test or final exam time is not for you to do revision. All right, you're supposed to answer questions. And for those who are not so sure, you can refer to your help sheet. So the help sheet only consists of the important key points, not everything. Yeah. That's why open book is terrible. Wow, you bring in so many books. Wow, flip. After you flipping, the exam is over. You have no chance to answer the questions. So, do the revision, write down the key points on the help sheet. Don't write down everything. Don't understand, terrible. Try to understand, make sure that you know what are important points and write it down if you want. All right? So one help sheet, midterm test, one help sheet, final exam, also one help sheet. All right? So to be more efficient, your midterm test is only one page, one side. Final exam, you have two sides. You cannot have more than two sides. One piece of paper. All right. Okay. And makeup test. So this is the valid reason. Beyond that, no makeup test. So reference. All right. Okay. So I ask the same question again. Are there any questions? No. Thank you. All right. Yes. Good. Okay. So now we start our journey of probability and statistics. Yeah. Yes. Yes. Okay. Probability. Hey, what is probability? Oh, by the way, I forgot. In fact, before we start, I want to know you a little bit better. How many of you are from School of Computing? Raise your hands. Let's show our hands. Oh, okay, thank you. How many of you are from Faculty of Engineering? And I believe there's a group called Computer Engineering, right? So it's half or part of it is School of Computing, part of it is Faculty of Engineering, right? Pure engineering, anyone? Engineering, computer engineering? Raise your hands. Oh, no one. So maybe they are in lecture group 1. Okay, any from Faculty of Science? Not too many. From other faculties, Arts and Social Science, and design and what? The formerly known as architecture. All right. Okay. So, School of Computing, right? Yes. The cream of the batch, right? Okay. School of Computing. So, can I assume that all of you have, for those JC path, have H2 mathematics? No. So, School of Computing does not require H2 mathematics. All right. Okay. Then, let me have some idea. How many of you have H2 mathematics? Oh, not too many, Okay. Okay, I'm not sure, but those who have H2 mathematics, do they have to take other modules like probability and mathematical statistics instead of taking this module? Right? Or no? Okay. Anyway, I have some idea of your background. How about those from Poly path? You must have at least one statistics module, right? Am I right? Or two statistics modules. Okay. Okay. So we try to assume less on the mathematics part, but we cannot run away. You need to have some basic knowledge about calculus, right? Calculus. Okay, so now come back to my first question. What is probability? Anyone have any idea what is probability? No, do you know anything about probability? Chance. Okay, chance. Yeah. They are looking from the dictionary, chance. All right. Basically, probability is a number to reflect how likely certain things happen. All right? So this number has to be between 0 and 1. All right? And usually people will think that probability has something to do with gambling, but in fact it's more than just gambling. All right. It may start with a problem that, because most likely, in fact, think of it, not just playing a game, a card games or board games or any games found in casino, but anything that may attach a probability. So, for example, okay, what is the chance that haven't happened yet? What's the chance that, or what's the probability that, all right, you will get an A in ST2334? 1. Yeah, I also hope that, but it's impossible. Everyone will have 1, yes? All right? So to you, all right, maybe you are very confident, but still we don't know whether you really got an A with a probability 1. All right? Don't say A, just what's the chance that you pass this module? 1, right? Check the past record, ask your seniors. There are failures. There are some fail this module. So, of course, it depends on yourself, all right? But what I'm trying to say is that probability basically reflects something that, all right, is not sure to happen or not to happen. It's somewhere in between. But the probability is a number between 0 and 1, and including 0 and 1. All right? Throughout this chapter, we'll try to appreciate or learn something about probability through some simple example. One very simple example is toss a die, a normal die. Everyone know what a die is, right? 1, 2, 3, 4, 5, 6. Normal one are 6 faces. You can find something have 12 faces or 20 faces, but it's not the one that we are talking about. We are talking about only a die with 6 faces. All right? And on 6 faces, number 1, 2, 3, 4, 5, 6. So that is our, a lot of examples that, many examples that we discussed will be based on this die. All right? Yeah, I don't know that so enthusiastic about the discussion of probability, or maybe the previous word, gambling, that will get you excited. All right, so it's just basically a number associated with how likely it occurs. And how to get this number, there are lots. I mean, part of the chapter 1 is to try to understand at least how to get this probability for certain event with a well-defined setting. All right? Okay, so this is an overview. We'll talk about basic probability concepts and definitions, and we start with the sample space and event. This phrase, sample space, is a little bit misleading. Sample, you know what is a sample? What is a sample? Huh? You don't know what is a sample? You know what's a population? Yeah. What is a population? A population, right? What is the population of Singapore? All right. So the population basically is a collection of people or a collection of things. All right. So when we talk about Singapore populations, then that means the people in Singapore. Of course, that definition, whether we should include those long-term stay or those PR or not. But basically, right at this point, usually when we refer to population of Singapore, we refer to the group of people that stay in Singapore for long term. All right? And we take a subset of the population that's called sample in statistics. But in probability, sample space is a collection of all the possible outcomes of an operation. So it's all. We'll come to that later. All right, operation of events. So complement events, mutually exclusive events, sure events, null events, all right? Unions of events and intersection of events. And counting methods. You know how to count? You think you know how to count, huh? But after this chapter, you know that you learn something, how to count. Yes, start from kindergarten. Kids learn how to count 1, 2, 3, 4, 5, 6, and so on. So now you are also do counting, but a more sophisticated way of counting. Multiplication principle and addition principle. Then permutation, combinations. These are terrible to some of you that find it very confusing. I try to make it clear for some of you. What are these? Permutation and combination. That is a way to do counting. All right? And then after we lay all this groundwork, how to count, how to do operation of events, then we move on to talk about probability. Before that, there are 3 ways to consider probabilities. And we spend most of the time talking about classical approach. What are the other 2? The other 2 are relative frequency approach. Simple example, I toss a die. What is the chance getting a 1? Do you know? Ordinary die, 6 faces with 1, 2, 3, 4, 5, 6. What's the chance getting a 1? No one knows that? Huh? 1, 6, huh? Thank you. So now you have the answer, right? 1, 6. Is it correct, huh? We don't know. When you ask the psychologist said there must be something that it's wrong. So 1, 6 is the correct answer, provided that. Provide what? Yeah, fair die. Fair dice, that means the outcome 1, 2, 3, 4, 5, 6 all have the same chance of occurring. So it's 1, 6. All right? All right? All these are classical approach. But if I don't learn this, so what to do? Give me a die. I toss it, get the outcome. See whether it's 1 or not. Toss a second time. A third time. Each time I check whether it's 1 or not. After all, like for example, I toss it 100 times. And then I see how many of the outcomes, how many of the tosses are 1s. All right? Maybe, let's say 10 times. Out of 100 times are 1s. Then I would say that the probability is only 0.1. All right, 1 over 10. Relative frequencies. How many times I do the experiment, how many times of the outcomes favor to my statement. In this case, it's 1. So I check how many 1s. All right? Yeah, 1 over 10 is different from what I believe. So maybe it's some kind of random fluctuations. So I try to toss more times. 1,000 times. Maybe 1,000 times is still not good enough. I toss it 1 million times. All right? And then record down the number of 1s. So what do you think about the number of times out of 1 million tosses that are ones. 1/6, close to 1/6. All right? You toss it one time, what's the chance you got a 1? When you do the experiment, either you see a 1 or you don't see a 1. All right? But if you toss it 1 million times, about 1/6 of the 1 million times, you will see a 1. All right? So that is the relative frequency approach. Because in some situations, some problems, you won't see. You cannot identify what are the possible, okay, you cannot identify equally likely outcomes. Like toss a die, you can say that is equally likely for these 6 outcomes. All right? Like, for example, what is the chance an accident occur at the junction of Clementi Road and, I'm not familiar, okay, the other side, Bonner Vista Road and, is it Cambridge? I don't know, okay, maybe more familiar. Orchard Road and Scotts Road, for those who are Singaporean, right? Know well, right? That's supposed to be the busiest junction. I don't know whether it's still the busiest junction in Singapore. Orchard Road and Scotts Road. So what's the chance that, what's the probability that an accident occur in that, at that junction on a particular day or particular hour? So how do we calculate? There's no way we can calculate it. So what we have to do is to look at the past record, all right, many hours, and then see whether accident occur at that point or not. So that is the relative frequency approach. The last one, subjective, is even better. Why I say even better? You can assign any number. Subjective, you don't have to justify it, so long as the number that you assigned is between 0 and 1. Right? For example, you know what is 4D, right? 4D. Have you paid 4D? Buy a 4D ticket? No? Okay, don't bother. Just buy, say a number, 4 digit, from 000 to 9999. Then someone, all right, or the house or the government or the totalization board, so they take some numbers out. So if the number happens to be the one that your ticket is, all right, then you win a prize, all right. So if I believe 1, 2, 3, 4 is my lucky number, I got a ticket 1, 2, 3, 4. So what is the chance that I will get a prize? Or just provide, the house provide one number. So what's the chance that I will win? So there are 10,000 numbers, 4D, right? From 000 to 9999, so it's 10,000 numbers, right? So my chance is 1 over 1,000. If I have money, so I buy from 0000 up to 9999, sure I will win. All right, I buy all the numbers. How much you pay for it and how much money you, prize money that you get, it's not a good business. All right. So my point is, if you just buy one number in this what we call 4D game, the chance that you win is only 1 over 10,000. Right? But if I believe I'm very lucky, no matter what number, 1, 2, 3, 4, I buy this 1, 2, 3, 4, it will sure the winning number. So I give the probability 1, right? Just like what you say, you want to get an A with probability 1. Yes, you can have it. So subjective probability approach means that you assign a number to the event. So what's the chance that I'm winning? I believe I'm so lucky that I believe the chance is 0.9, 90%. All right? So of course the chance I fail will be 10% only. That's subjective. All right? So of course there's a branch of probability theory derived from this called Bayesian approach. So they assign a higher probability or higher distribution to the events, and then collect the data, then modify your belief on this probability. All right? So just doing all this, and then this is another branch of statistical inference. Okay? Then axioms of probability. You know what is axioms? I don't know whether in in computer science, whether they have these axioms. They must have some axioms. Axioms means basic foundation, or basic property that we just have to accept it. All right? So, so there are three axioms of probability for which we accept it. We don't challenge it. Don't challenge them. And we believe the other properties about probability can be derived from these axioms, from these basic properties. All right? Yeah, basic property of probability, and then we talk about conditional probability. This is a hard topic, conditional probability. Some of you may confuse about this conditional probability. And finally, multiplication of probability and law of total probability, as well as Bayes' theorem and independent events. All right? The later part of this chapter got more interesting. Okay, sample space. Okay, by the way, do we need a break? No need. I can talk and talk, all right? 3 hours. Unfortunately, I only have 2 hours, or maybe even 1 hour, 30 minutes. All right? Okay, so at least the time being, no break, right? Since those who want break, they don't voice out. So you can leave anytime you want for whatever you do, but come back. Okay, so let's continue. Sample space and sample point. So first of all, we are talk about observations. All right, so we refer to anything that we can record down as observation, be it numeric or just categorical. So, for example, a simple example, right? I want to know the height of everyone. All right, so height itself is an observation for each of you. But I can also want to know the gender of individual. Gender is not a number. Gender is male or female. All right, or even whether you wear glasses or not. All right, so these are categorical. So this kind of information, we call it observation. All right, so we perform an experiment, but in fact this is not the real, the general understanding of experiment. Just do something that will have some observation, generate some observations. All right, so a procedure that generates data, generate observation. Then we call that an experiment. All right. So sometimes you don't really have to do it. So, for example, I want to know whether you are the gender of an individual. So I just look and check whether, or ask them to fill in the survey form whether what is the gender. So no real experiments are performed, just the way to generate the data or observations. All right, sample space. All possible outcomes. Remember, although the word sample is used, but sample space means that it is the set of all possible outcomes. Now here is you have to pay attention. All possible outcomes. I toss a coin. All right? So what are the possible outcomes? What are the possible outcomes for tossing a coin? What? Thank you. Head or tail? Head or tail, right? Can it be two heads? I did not mention whether it's fair or not, so there's a possibility 2 heads. But, okay, but in general, it's just head and tail. But this is because you think of, you toss the coin, what is the face, whether head or tail, all right, on the face or the top face, the face up, all right? That is the outcome that you want to, or you are interested in. But let's say, if I'm interested in, I toss a coin. Toss a coin. Unfortunately, I forgot to bring a coin. I toss it. All right? So I look at the outcome. It's a head. All right? So the outcome is a head. Of course, the outcome can be a tail. But maybe I'm not interested in whether it's a head or a tail. I'm just interested in how far, what's the distance it lands from a reference point. So the reference point may be where I stand. Look at how far it lands. All right? Now, so in this case, what I'm interested in is the distance. It's not head or tail. It's just the distance. All right? So what are the possible distance that we have? From 0, it dropped at the reference point, or up to infinity, theoretically speaking. But physically, even you are Olympic sportsman, you cannot throw a coin more than, let's say, 100 or 200 meters. All right, so theoretically speaking, all possible outcomes in this case is the distance, anything bigger than 0. But of course, it's very unlikely to have a distance beyond maybe, let's say, 500 meters. All right. It's not a gun and not a bullet and not a missile, so somewhere it lands. All right. So my point is, when we talk about all collection of all possible outcomes, you have to be aware of what you are interested in. Toss a coin, most likely we're interested in the face, whether it's a head or the face up, whether it's a head or tail. But in some other circumstances or some other scenarios, you may be interested in something else, where it lands. All right. Okay, so sample space basically is a collection of all the possible outcomes. All right, here is some example. Toss a die. All right, we're interested in the number shows on the top face. So it's 1, 2, 3, 4, 5, 6. Now, if you are not interested in the number, you are just interested whether it is an even number or odd number, then in that case, the sample space consists of only two elements, even and odd. Even and odd. All right? So it depends on what you're interested in. So toss 2 dice. If you're interested in the number of top faces, then they're all open. How many are there? 36. Huh? Now I want to ask, why I have to write it 1, 2, and 2, 1? Different what? Different orders. Yeah, yes, it's different orders, but why? Now think of it, if I have 2 dice, you cannot distinguish them. I throw it, so you got the 2 numbers, all right? Right? Now, so if I got one is 2, the other is 1. You don't know which one is 1, which one is 2. But if I paint the 2 dice with different colors, let's say 1 red and 1 blue, then you can have the red, let's say the first one represents the red die. So the red die got 1 and the blue die got 2. It's different from the red die got 2 and the blue die got 1. That means these two represent different things. So yes, we have different order. So there's some meaning about the order because it represents 2 different dies. But in general, we just have the same white color, white dies. So when you toss it, you cannot tell the difference. All right? So whether 1, 2, and 2, 1, which die got 1 and which die got 2, you don't differentiate. But here we try to assume that we know that they are different dies, or you can call the die 1 and die 2. All right? So that you know the first coordinate referring to the outcome, the number shown on the die 1, or easier to paint it in different colors. So the second one is die 2. All right? So that 1, 2, and 2, 1 represent 2 different outcomes. All right. Why we have to do that? Because we make sure that all these 36 outcomes are equally likely. If you drop this consideration of the ordering, which one got 1, which one got 2, then they are not equally likely. Right? Think of it. What's the chance getting 1, 1? That means both die are 1s. And just getting 2 dies, one of them is 1, the other is 2. Which one is more likely? From experience, we know that. All right? Getting 2 die of the same number, the chance is lower than getting different numbers. All right? So this way of presenting is to make sure that all the outcomes here we mentioned are equally likely. Flipping a coin, so this one is very, very sure that we have two operations, one follow the others. So if the first one is to toss a coin, if it is a head, then we continue to toss the coin a second time. But if it's a tail, then we change track. Now we don't use the coin, but use a die and toss the die. All right? So what are the possible outcomes? So there are 8 of them. The first one is H, then you have only 2 related to H. Then if the first one is a tail, then you have 6 outcomes related to this. So these are the possible outcomes. So the sample space consists of these 8 elements. So this one need to have an ordered pair. All right? The first one referring to the toss the coin the first time. The second outcome depends on the outcome of the first one. All right? Strict times index. All right? So all possible outcomes. This is only a set. This is just a set, a strict times index for a few days. But strict time index has been around for quite long a period, so that a lot of outcomes. But in fact, the strict times index is supposed to be range from 0 to infinity. All right. Hey, what is strict times index? Index, right? Can it be negative? Huh? Anyone who come across it? Can strict times index be negative? Of course, if you check it, it's always a few hundred, maybe even few thousands. Do you have any idea what's the highest strict time index? 5,000? 10,000? Anyone knows? Yeah, maybe you don't have the money to buy stocks yet. Okay, I'm not sure, but it's about 3,800 or 4,000. I believe so. Okay, I'm not business people, so I don't know. Right? But it cannot be too big. But it cannot be negative because the index is based on all index are like this. It's based on reference date, the value of the strict times. Oh, yeah, thanks. You are checking, all right? Or just watching for your social Okay, thanks. Okay, so all things called index has a reference. So Straits Times Index is the value of the whole market, or based on, it's not the whole market, based on a basket of stocks, all right? And compared with the, not necessarily the same basket, but related to certain date. I forgot the date that they used, reference maybe 20 or 30 years ago, all right? So if the Straits Times Index is still about 100 or 200, then it's very bad. That means compared with 20 or 30 years ago, the reference date, your index is only 2 times the value of the value at that point, all right? So right now it's 3,000 something, all right? So it's about 30 times, all right? So my point is that this possible space, or this sample space, should be any number bigger than 0, all right? But it cannot be negative. All right, so here, another experiment consists of drawing 2 balls, all right, and containing 1 blue, 1 wet, and 1 white ball. So these are the possible outcomes. So again, I use an ordered pair to represent if the B is in the first coordinate, it means that the black ball is drawn in as the first ball, all right? So sample point is just a possible outcome. That is called sample point. It's just an element in the sample space. An element in the sample space. And so in this case, sample points are 1, 2, 3, 4, 5, or 6. And in this case, as a sample point, a sample space, then the sample point is only 2 of them, either even or odd. So in this example, so the sample points, all this, one of this ordered pair is considered as a sample point. Now, I want you to understand that a sample space is the collection of all the possible outcomes. Sample points are those outcomes, all right? Then, this one, these are the sample points, all right? Okay, events. Now, events is a subset of the sample space, which means that it consists of some of the sample points, all right? Of course, one sample point can be considered as an event. So an event is maybe just have one sample point, or may have a bunch of the sample points, or may have all the sample points. It's still called an event. It's just a different event, all right? So in this case, an event, usually we need to describe the event. So for example, an odd number occurs. So if the sample space that we're considering is 1, 2, 3, 4, 5, 6, then the event is 1, 3, 5. If the event is an odd number, so it's 1, 3, or 5. If any sample points, all right, here occurs, then we say that an odd number occurs. So a number greater than 4, not including 4. So the event is 5 and 6. If the outcome turned out to be 5 or 6, then we say that a number greater than 4 has occurred. But if the sample space is even or odd, then an event of odd number, all right, means that there's only one sample point, just the odd, all right? So, rolling a pair of die, and the event A is the sum of the 2 dice equal to 7. So we go back and check what are the sample points that will give us a sum equal to 7. Okay? So these are the sample points. 1, 6, 2, 5, and so on. That will give a sum equal to 7. You can check. 7 have 6 sample points that belong to this event. If you the sum equals to, let's say, 2, sum equal to 2, then there's only one sample point that will give us the sum equal to 2. So in other words, it's more likely to get a sum equal to 7 than get a sum equal to 2. All right, in this example, suppose an event that no die is thrown. So in that case, that means the first outcome of the experiment must be a head, so that we won't toss a die. So in other words, there will be 2 sample points. That means, that refer or related to the event that no die is thrown. Because the other sample points are something like this. The other sample points are E1, E2, T6, and so on. So these are all referring to the sample points with a die. So this is another example. All right. Toss 2 die. So all possible sample points are these 4. And if my event is getting no head, 1 head, or 2 heads, basically cover everything. All right. So this is the sample space. This is the event, which is exactly the same as the sample space. All right. Getting 1 head or no head, and getting 2 heads or 2 tails. So all these are the possible events. Okay, so we have some idea what is an event. So now we try to distinguish among events. So there are 2 types. One is simple events, which means that the event consists of only 1 sample point. A compound event means that it consists of more than 1 sample point. All right? So it's exactly 1 outcome. All right? So in this case, an odd number occurs, consists of 3 points, 1, 3, and 5. So this is a compound event. Obtain a number greater than 4. It is compound event because it consists of 5 and 6. But get a 6, then it's a simple event because it has only 1 sample point. When I say 1 sample point, it's referring to this sample space. All right? So if the sample space is like part B, only even and odd, then getting an odd number now becomes a simple event. So sum equal to 7 is a compound event. Sum equal to 2 is referring to 1 sample point, so that becomes simple events. All right. Now why we have to consider all this? Because later on we'll try to assign a probability or somehow get a probability to each sample point. So simple event, the probability of a simple event to occur is very easy. It's just equal to the chance that that particular outcome occurs. But when you come to compound events, then you have to do something about it. It's all complicated. All right, so these are examples. And this one, if T is the lifetime of certain electronic component, then A referring to T between 0 and 5, which means that the lifetime is between 0 and 5 years old. It can go beyond that, but our interest is this event. That means the lifetime is shorter than 5 years. All right, so sample space is also an event, but we call it a sure event. And if, I don't know whether you still remember that, this notation represents a set with nothing in it, no elements in it. We call it empty set. All right, empty set is in event is referring to a null event or impossible event. That means you cannot find any sample points that belong to that set, all right, empty set. So therefore, it's impossible to have that occur. So we call it null event. Okay, operations with events. Okay, so there are two operations, or three, including complement. So first one is union. Union is something like add together. All right. So A union B are two events. A union B means that you collect all the sample points that either belongs to A or belongs to B. But can X belongs to A and B together at the same time? Yes, it will be included. So long as you find anything. So for example, this part belongs to A. Is this part belong to A? Yes, right? But it also belongs to B. So this is A intercept B. And this whole thing is A union B, because any of the points within this region, right, they belong to either A or B. All right? And in fact, also some of them belongs to A and B. So this is A intercept B. A intercept B means that it has to be has to belong to A at the same time it belongs to B. Just belong to A doesn't count. Just belong to B doesn't count. It has to belong to both A and B. So what happened to this? What is the intersection now? No intersection. Empty set. All right? So this intersection is empty set. And in fact, we have a name to given to this situation. This A and B are called mutually exclusive events. That means if we know that A has occurred, then B cannot occur, because A and B have no sample points in common. So if A occurs, B will not occur. But in this case, then this one will belong to A and B. That means A has occurred, B can also have a chance to occur. Then the third operation is complement, which means that we are considering those points that does not belong to A. So it's in the sample space, but does not belong to A. Then we call it A complement. Now, it's just definition, but it's very useful. For example, if I asked, toss a die, what is the chance getting a number greater or equal to 2? Then that means you have to look at the chance getting a 2, getting a 3, getting a 4, getting a 5, getting a 6. A lot of calculations if it's not equally likely outcome. But on the other hand, okay, getting a number greater or equal to 2, all right? Greater or equal to 2 for toss a die. The complement event is a number less than 2, which means that it is x equal to 1. So I don't have to calculate the chance of getting a 2, 3, 4, 5, 6. I just calculate the chance of getting a 1. And then subtract from it. I will get the probability of x greater or equal to 2. So this complement event is useful in calculating the events. So here are some examples. Now, if you try to appreciate all this theory or these formulas that we mentioned, use some example to help you to understand it. So a simple example is like this. I consider tossing a die. So the sample space only 6 points. So event A, 1, 2, 3. How to describe event A? Or a number less or equal to 3, or a number less than 4, right? All right. Okay. And how about B? Odd number, right? How about C? Even number. All right. Oh. Yeah. Okay. A union B. That means you have to find some sample points that belong to A or belong to B. So I have to consider 1, 2, 3. These are from A. And 1, 3, 5, 1, 3, 5, this belongs to B. All right? So I put them together. So 2, sample point 2, belong to A, but not belong to B. But it's okay. We're talking about A union B, so we include all this. All right? And A union C, 1, 2, 3, 4, 6. B union C turned out to be everyone. So B union C is equal to the sample space. So A union B union C, because this is equal to S, A union S is equal to S. I have this question. A union B union C. When you write program or when you do the operation, you cannot, okay. Of course, one way is that you strictly write down all the elements belong to this A union B union C. But if you want to do it step by step, all right? So naturally, you will do this first. Do this union first, right? Right? And after that, you got the results, and then union C, right? I think this is the natural way to do it, from the left to the right. So you union A and B, after that you union C. But do this. Of course you can do it. The question is whether they are the same. Is it the same? Whether I do it A union B first and then union C, or I do the later part first. All right, B union C. After that, I then union A. Okay, you tried it out, but the answer is yes. All right. Okay, yes, for this example. Then the next question is it true in general? All right, is it true in general? That means for any situation, is it correct? All right. So I leave it to you to find out. All right. Okay, and in fact, there's a name for it. There's this rule or law associated with this. Whether you do A union B first or B union C first. All right. So you check. The answer is yes, right? For this one. But is it true in general? Okay, we still keep this example. Now we look at intersection. A intersect B, A intersect C, and B intersect C is empty set. All right? So we work on the A intersect B first. So the answer is empty set. If you work on B intersect C first, you also get the answer empty set. So again, intersection, this particular operation, also have these properties of whether it doesn't matter whether you intersect A intersect B first or B intersect C first. Which one you operate first seems to give you the same answer. Whether it's true in general. In this example, yes. All right? Both this and this are the same. All right? Now, so it's always like this. I have two operations, union and intersection. So union is to operate two events. So just now we discussed, okay, I union three events. I also discussed how to intersect three events. And the order seems not important. Whether you intercept the first two first, or you find the intersection of the second and the third, it doesn't matter, seems, all right? Now, so now I mix them. Intersect and union mixed together. So this one, A intersect B, union C. All right? So I got this answer. And if I union first and then take the intersection, the answer is not the same. Okay? So So this is the order of operation. Which one do first is not the, I mean, they will give you different answers. All right? So you have to pay attention to this one. All right? The three events, the operation are the same. It doesn't matter which you do first. But then if the operations are different, intersect and unions, then which one to do first is will give you different answers. So try to avoid confusion. If you write it like that, people by default, I think computer programmer knows you must set some default. So people will start operate, do it from the left to the right. So do the intersection first and then union. But in order to eliminate the confusion, please put a bracket there to indicate which one you want to do first. Although by default, people usually will do it from the left to the right, all right? But please, if you really want to do, put a bracket there so that we know that we have to do this, right? Okay? I think I once tried this one. Or 2 plus 4 times 3. Yeah, sorry, maybe this one. 2 plus 4 times 3. For humans who learn arithmetic, multiplication first, 3 times 4 first, and then add 2, right? But if you do it from the left to the right, you will add 2 to 4 first, and then multiply by 3. All right? So my point is, make sure that others will know what you mean. So put a bracket will make things clearer. All right? So if you really want to have 2 plus 4 first, put a bracket. So similar to this. All right? Okay, so just make sure that you remember this fact. Mixture of intersection and union will give you different answers for different order. Which one do first? So this is just an example. This is another example. Talk about complement. So B turned out to be C. B complement turned out to be C. So A complement intercept B complement. What does that mean? It means that I want to find some sample points, some elements that at the same time does not belong to A and not belong to B. All right? So you look at this, obviously 4 and 6 are not there. So the A in complement intercept B complement is 4 and 6. On the other hand, we look at A union B. This is A union B. And the complement will be 4, 6. All right? So this is to illustrate this very useful properties of operation. A, this means that it belongs to A or B. Complement, that means it does not belong to A. At the same time, it does not belong to B. All right? Because they say that it belongs to A or belong to B. The complement saying that it does not belong to this set. All the elements or ons in this set referring to belong to A or belong to B or belong to both. Only those outside A and B. All right? So it must outside A at the same time outside B. So you have to have these two together, and you can see that they are the same. All right? So, in fact, this is true in general. We can show that. Okay, mutually exclusive events. So, so long as two events has an intersection equal to empty set, we call it mutually exclusive events. And what it means is that the two events cannot occur simultaneously. If one event occurs, the other one won't occur. Just like toss a die, you cannot have even and odd number at the same time. The outcome has to be either odd or even. It cannot be odd and even at the same time. So odd event, an event of odd numbers and an event of even numbers, these two are mutually exclusive events. So a picture like this. So I think you can read this yourself. Okay, union of n events. So just now I talked about union of two events or union of three events. So now we extend it to n events. So union of n events denoted by this, all right, which means that this union consists of all the sample points that these sample points must belong to at least one of those events. It can belong to two of this, three of this, or all n of them. But it must at least belong to one of these events. Then it belongs to this union of n events. By the way, you must understand this kind of symbols that mathematicians use to write down things. So this union, all right, means that we are doing an operation union. And what are the events that involve? It denoted by AI. AI is, okay, the I is the subscript to identify the event. So I equal 1, it means A1. I equal 2, it means A2, and so on. So how many indexes are there? It's from 1 up to n. That means I can be 1, can be 2, can be 3, up to n minus 1, then n. So that A1 up to AN events. And the operation is union. So we union all this. So for example, if I write down summation I from 1 to 10, I squared, then what does it mean? It means that we are adding a number, adding a bunch of numbers. Each one is I squared. And I start from 1 up to 10. So it's 1 square plus 2 square plus 3 square up to 10 square. Starting index, ending index. So that's how we write it. So if I write, this is what we mean by multiply. This is sum plus. This is multiplication or product. All right? So it's 1 square, 2 square, up to 10 square. Multiply all this together. So for this, it's union. So it's A1, A1, A2, up to AN. And the operation is union. Union. All right? So that is how we... So intersection, the same thing. All right? So intersection can be represented by this. And this means that it is an event. The elements or the sample points in this event must belong to all of these AIs. All right? It has to be in A1, it has to be in A2, has to be in A3, and has to be in AN. All right? That's what it means by intersection of n events. Okay, some basic properties about operation of events. So follow from the definition. Can you find some point belong to A and A complement at the same time? Of course not, so it's an empty set. All right? Then, the intersection of empty set and A is equal to empty set. Because you cannot find anything that belongs to empty set and A at the same time. Empty set is empty, nothing in it. How can you find something that common to A and empty set? A union A complement equal to S. Complement of A complement is equal to A itself. It's just like, okay, A, take the complement, so you got this one, and then take the complement of A complement, you go back to A. All right? So we have already discussed this one. If you look at A intercept B, That means common to A and common to B. But then you take the complement. That means you find something that is not belongs to A and B at the same time. In other words, it can just belong to A but not B. It can belong to B but not A. Of course, it can be not A and not B. So that's why it's equal to A complement union B complement. Similarly, the complement of A union B is A complement intercept B complement. Now, I would suggest that you think about how to interpret these two so that you remember these properties. It's very useful in calculating the probability. All right? So, this is how to do it. So, if like this, it looks as if, although it's not exactly the same, 3 times 2 plus 4 is equal to 3 times 2 plus 3 times 4. So it's like that. All right? But it does not mean that union is equivalent to multiply and then intersect is plus. But it can be shown that it's A union B and then intersect A union C. All right? On the other hand, A intercept B union C is the same thing. So it's A intercept B first, and then look at A intercept C, and then take the union of it. So in other words, although I look at B union C, but now I want to look at B common to A, all right? And then also look at C common to A, and then union these two. All right? That's what it means. This is very useful and very intuitive. Looks very complicated, but if you draw the Venn diagram, all right, this is A and this is B. So A union B is this part. So what we are saying here is that, okay, this is A. How to describe the rest? How to describe this part? It belongs to B, right? Right? It belongs to B. But again, this part also, this also belongs to B, right? So this is not just belong to B, but at the same time belong to something else as well. What is it? Those points in this part, or those sample points in this part, it belongs to B as well as belong to A complement. It does not belong to A. So we have to take the same. So A union B intersect A complement. Okay, just put these two pieces together. These two pieces, no overlap. One is the whole A. The other one is those B, but not belong to A. And put this together is A union B. And finally, this one is even better. What it means is that, okay, we are talking about A, so I divide A into two parts. This is A common to what? Common to B complement. It does not belong to B. Well, this part of A, it belongs to A, at the same time belong to B as well. So I have to put these two together. A intercept B complement and A intercept B, put them together. All right. Then these two that we mentioned earlier, the union and intersection, okay, it's not here, but it can be extended to n events. All right, and it's called De Morgan's law. All right, union of n event, take complement, is the same as taking complement first of all these events, then intersect together. The intersection of all these events, take the complement, is the same as taking complement of each event, then put them together, union. Okay, I think the examples, you can read it yourself. All right. A is a subset of B, contained in B. This is what I'm trying to do. This is more important. So, in set theory or in event, if we say that two events are the same, A equal B, it means that A is a subset of B. Means that whatever you find in event A, you can find in event B. So A is contained in B. On the other hand, whatever you find in B, you can also find it in A. So B is contained in A. So if these two occurred, then it means that A and B in fact are the same thing. Whatever you find in A, you can find it in B. Whatever you find in B, you can find it in A. So in other words, these two events are the same, are equivalent. So A equal to B. All right? Event A equal to event B. So you can check all these examples. It just, okay, you first of all, you work out and then see whether this statement is correct. All right? Okay. So, yeah. Okay. Yeah, it's not good time to start another session. So we stop here. Oh, hooray! Yeah, there are two implications. One is that my suffering is over. The second, I am happy that I learned something today. All right. I will interpret the second one. All right. Okay. I hope I still can see you this Thursday. But I won't get pay more if you come or not.